Shall I put the lights down?
Yes.
Should be clearer.
That'd be good, yeah.
Everyone happy with that? So good evening, thanks for coming. My name's Carl. I'm doing a part-time Ph.D. here at the University of Kent at Canterbury in the Centre for Astrophysics and Planetary Science. And my studies really involve mainly numerical simulations of supersonic jets with a specific interest in jets from active galactic nuclei, or AGN jets, or galactic jets. So this, for example, is an illustration. It's not an image, and it's showing a galaxy with bipolar jets, and it's driven by a central black hole. And the inset image here is a snapshot of a hydrodynamic simulation with the jet along the central axis there, showing pressure variations along the jet and into the surrounding ambient. So I'm definitely not an observational astronomer. In fact, I think from what Tim was saying, most of you will probably know more about telescopes and observing than I would. I think my first experience of observing was at school when I had a Christmas present of a telescope when I was making observations of the moon and seeing how clear the craters were and the shadows cast, etc. And one thing I was surprised about was how quickly the moon moved out of the field of view. I kept having to move my tripod around, and I remember thinking at the time that the moon is really whizzing around the Earth. And a little bit later, I managed to have the opportunity to look through a 12-inch refractor at a small observatory, which happened to be pointing at Andromeda. And I've seen pictures of Andromeda before, but it was the first time I was actually looking at it live, if you like, and those photons had traveled all that distance through space and ended their journey in my eyes, looking at. So I felt a connection there, but obviously not enough to become an observational astronomer. But in research in astrophysics, it's important to have a balance between theory and observation. And you can have research where there's lots of observations with underpinning underlying theory, or mostly theory, simulations, maybe even experiments, which are informed and constrained by observations. So they are very important. So I've had to do my homework here on some observations, and what I've done is I've put together some slides, and I've tried to split them into three parts for you. First of all, to talk about a little bit of theory of active galactic nuclei and jets with some supersonic shock structures. And then a second part about observations. So I've chosen three relatively nearby galaxies which have fairly good resolution, because normally the resolution is not very good with AGN jets, which is why there's a lot that we don't know about them. And while I was doing that, I thought I started a thought experiment involving an alien astronomer. So I'll share my thoughts with you on that as we go through. And then the third part is I'll share a little bit of the research that I've been doing here at the university with my supervisor, Professor Michael Smith, also from Canterbury. And I'd like to explain a little bit about the actual work that we've been doing, the research work we've been doing. So that's my plan for this evening. So beginning with some theory, and I tried to choose my words very carefully because it's very easy to talk in absolutes. Theories are just that, they're theories. There's some information from observations, etc., to support various theories, but often it's very difficult. You need to choose your words very carefully. So, for example, it's believed that most galaxies have a supermassive black hole at the center of them. And by supermassive, I mean at least 1 million solar masses. So for our galaxy, the Milky Way, it's estimated to have a black hole mass of 4 million solar masses. And this is the sort of thing that it's believed drives the jets. The central black hole has an accretion disk of hydrogen where gravitational energy is converted into high temperatures, which produces high luminosity, produces ionization, electric currents, and therefore magnetic fields. And it's been shown for many years that those magnetic fields are capable of generating bipolar plasma jets that take some angular momentum from the accretion disk and material from the disk and send them out along these jets, which can extend for many parsecs, hundreds of parsecs, and for millions of years. They radiate across the electromagnetic spectrum, but they're normally viewed at radio frequencies or X-rays. Depending on your line of sight, you may only just see one jet, one of the two jets. And that is often the case. And there's an example here at the top where it says blazar. So that's where the jet is actually pointing virtually along your line of sight. So there's a number of classifications of jet. Fanaroff-Riley classifications. These have been established for some time. For FR2 jets are the most powerful. They tend to have a small opening angle, and they can penetrate the ambient medium surrounding galaxies. The ambient medium surrounding galaxies isn't a vacuum, an absolute vacuum. It has mass, it has density, it has pressure. It's very, very small. But for example, for many galaxies, there's several times more mass in the ambient surrounding a galaxy than in the central galaxy itself. So for FR2 jets, they're very powerful. They can penetrate without engaging very much in the ambient, and they can terminate in hotspots, bright spots, over hundreds of kiloparsecs. The FR1 jets tend to have wider opening angles, etc., we think, and engage more locally with the ambient. So the bright spots, the bright engagement with the ambient occurs much closer to the host galaxy, and there's a fainter jet beyond. And more recently, an FR0 classification has been made where the jets are in a sort of parsec scale. So you're really going from hundreds of kiloparsecs to hundreds of parsecs to just a few parsecs. That's trying to classify them, but there are all sorts of variations. You can have precessing jets that turn on and off, leaving trails in the extragalactic environment that show a record of previous episodes, if you like. But in these jets, we see luminosity knots, and these are believed to be shock fronts. And there's some observational evidence for that. So I'd just like to give you a little bit of theory on some of the on supersonic jets, which are entirely scalable, from galactic jets to protostellar jets to the jets from rocket engines and jet aircraft. Because we see these luminosity knots and we believe them to be shock fronts, you get that when you have what's called an overpressure jet. So the pressure within the jet is higher than the ambient outside. So that's the sort of thing that we've been doing our research on. So this is an example of a low overpressure jet. So you get oblique shock fronts. When the jet is launched and is traveling from left to right, the jet wants to expand because it's at higher pressure than the ambient. And the pressure falls to that of the ambient and then gets redirected via a shock front. So supersonic flows change, not via step changes. So they need shock fronts in order to do that. And post-shock, there's a decrease in velocity and an increase in pressure, temperature, and density. So there's an interchange between kinetic energy and enthalpy. And surrounding the jet is an annulus of turbulence, and that has Kelvin-Helmholtz waves, just basically waves, which can influence the structure within the jet. So the position of these shocks can actually oscillate. So although there's a constant flow, supersonic flow going from the left-hand side, there's a lot of dynamics within a supersonic flow. And it's exaggerated here greatly, but eventually you end up with turbulent flow. So that's for a low overpressure jet. And that's the sort of thing you see in exhaust from a fighter aircraft, for example. So this is the other sort of shock structure, is a Mach disk. So this is a normal shock. Here in 3 dimensions would be a disk. And this is a high overpressure. So again, you get expansion from the jet. This is a Mach 2 jet example, expanding initially until the pressure falls to that of the ambient and then gets reflected back towards the central jet axis. But because the angles, the shock angles aren't steep enough, there's a shock front, a detached shock front, occurs because the pressure falls so low. Post-shock, there's a step decrease in velocity, but this time it's subsonic, and a much higher increase in pressure, temperature, and density. So it's much higher acceleration then, back up to supersonic speeds until the next shock front. And if the pressure is particularly high, you will only get one shock front because there's just too much turbulence downstream. So that's just to explain the two sorts of shock fronts that we observe on all sorts of scales. And that's an example of a high overpressure with a Mach disk from a very powerful rocket engine. So that was a very quick explanation of some of the theory behind the driving force behind galactic jets. We believe them to be supersonic. The speed of sound in the extragalactic medium is about 1,000 kilometers a second. And these shock fronts, we believe, are the cause of these luminosity knots that we see from our observations. So the second part, I'd like to go through, in terms of observations, I've picked on three galaxies where the resolution is sub-parsec. For most jets, it's very difficult to get the resolution that we need, and there's lots of unknowns in terms of the galactic jets. So beginning with how we take these measurements, we use something called very long baseline interferometry. So this is where we take radio telescopes around the world, looking at objects at the same time. So effectively, our telescope, our radio telescope, is the size of the Earth. That's how we get the resolution that we're looking for. And it's at radio frequencies. If you remember, I said jets radiate at all frequencies, but generally they're observed at radio frequencies because they're most intense. And that's just one example of a radio telescope array. So these need to be coordinated around the world, and the more you can get into your array pattern, the better. If you look online, there's a program called Mojave, monitoring of jets from active galactic nuclei using very long baseline interferometry array experiments. And there's lots of observational information there that's been recorded over 20, probably nearly 30 years now. So the first of the three galaxies I'd like to talk about is Cygnus A. It's 750 million light years away. So it's quite a long way away, but it's one of the most powerful radio sources in the sky. In the constellation of Cygnus, round about here, near one of the bright stars in Cygnus. And this is a composite image. The white is optical, the blue is X-ray, and the red is radio waves. So at the center is the elliptical galaxy. These are the hotspots at the termination of the jets. It's got a high angle to our line of sight, so there are basically two jets visible. And these regions, inflated regions, are heated, and really that's where the term radio galaxies come from, because they're emitting at very intense radio frequencies. So these are sort of the images you might find when they look at like the Mojave program, and looking over a period of time, and they identify the central accretion disk, if you like, and various luminosity knots along the jet length. And they also look at them over a period of time. So they do tend to move around a little bit. Like I said, in normal supersonic flows, you will find shock fronts that aren't entirely stable. They will oscillate. So it does sort of chime with the supersonic flows that we can find. And this is some of the information I've managed to glean. I won't go through all of it, but the mass of the central black hole is 2.5 billion solar masses. And the event horizon radius for that black hole is about a third of a light day. So that's about the distance from the Sun to Pluto. The jet length is quite long, 150 kiloparsecs. And for me, finding out this information, you know, the jet base is quite a long way away, so it's not very precise. It's something less than 35 light days. That's the sort of unit that you can deal with at that scale. And from looking at various polarized light, you can detect magnetic fields. And there's evidence of a parabolic shape of the jet because of poloidal magnetic fields. So the jet diameter radius is increasing, and the jet velocity is being accelerated out to a number of parsecs, a few parsecs, and then it becomes a conical jet. And that's something we've seen in some of these local AGN jets. So we don't see it in all jets because they're just too far away. And that kind of fits in with some of the theory that we have about AGN jets, about the galactic jets. And this is an FR2 jet. So it was at this point that I started thinking about doing a thought experiment. And I was thinking, we have a view of Cygnus A. What if there's an alien astronomer looking back at us? Because if we could ever meet, we'd have a lot in common. If we get over the language barrier, we both know about observing stars and star formation, binary stars and supernova. They know about black holes, different types of galaxies, the expanding universe. Their physics would be our physics. their periodic table, what would be our periodic table. So I kind of thought they would have a lot in common with an observational astronomer. But then I thought about the distances. You know, it's a huge distance. And when I was thinking of just the scale of the base of the jet in terms of light days, and I was looking on social media at the time, and there was something about Voyager 1 that happened to be there. And Voyager 1 was launched in the 70s and is to take pictures of the outer planets and has left the solar system. And it was launched actually on the 5th of September, Monday the 5th of September, 1977. And that was actually the first day I attended the sixth form. And it's been traveling at 38,000 miles per hour, which is about 17 kilometers a second, every second. And at this point in time, it's only traveled, well, I say only, it's traveled about 0.9 of a light day. So it hasn't even traveled one light day. So if light had left Earth at the same time that Voyager 1 did, light would have got to where it is today before I'd finished my second day in sixth form. So distances are just too vast. So then I thought, well, what if this alien astronomer was an advanced alien astronomer? Maybe they'd have 1 million years of experience under their belt, and they could actually see Earth, and they could see the British Isles, and they could see us. Just a thought experiment. And when you think about it, the advances that we have in observational astronomy now, it's only been 416 years since Galileo was the first human ever to look through a telescope. And he was looking at craters on the moon, drawing images of craters, and seeing images very similar to what I would have seen when I was at school. So I thought, so I had to do a little bit more homework and think, what would he see? Well, what would he or she see? And if you look back, they would see something like this. They wouldn't see the British Isles. They'd basically see one supercontinent centered on the center of, on the equator. And what would become the British Isles is in the south, in the southern hemisphere. So they wouldn't see the British Isles. So then I thought, well, would they see us? I'm not very good on history. And the bottom line is no, because there's only microscopic life back 750, 60 million years ago. And that's an example of a microscopic sponge. So they wouldn't see the British Isles, and they wouldn't see us. So moving on to my second galaxy, which is M87. M87 is 50 million light years away, so it's about 10 times closer. It gets a lot of attention, especially when you have modern telescopes like the Event Horizon Telescope, James Webb Telescope, etc. Gets a lot of attention, and quite rightly so too. So it's in the constellation of Virgo. And this is a composite image. It's a optical and X-ray. So this is the central galaxy. These are just some local stars. And this is just a single jet. So it's got quite a shallow angle to our line of sight. And these are some of the knots, the luminosity knots that I was talking about. This jet's about 1,500 kiloparsecs in length. So, like I said, most the galaxy jets we don't fully understand because of the lack of resolution. So looking at nearby jets can be very informative. And this is the sort of image you can get from the Very Long Baseline Interferometry. The central accretion disk, very high temperatures, creating these magnetic fields driving out a jet that's got quite a wide wide angle. It's an FR1 jet. And you can get some very precise measurements in terms of radio intensities. But it's only at that one frequency. When they look at jets like this at radio frequency, they tend to be only one or two, just a handful of radio frequencies. So it's a partial image. So these are some of the information I managed to glean from various references for M87. Supermassive black hole with 6 billion solar masses. I think from the literature, the highest I've seen is something like 46 billion solar masses, so absolutely massive. Small sky angle. The event horizon corresponding to the black hole is about half a light day. So that's about twice the distance from the Sun to Pluto. And the accretion disk temperature is very high. It's 1,000 times that of the center of the Sun. So this is why, for example, quasars, the central nucleus, the active galactic nucleus, can outshine the sum of the luminosity of all the stars in the host galaxy. And for the jet radius, it's around about 2 light days. Got very high jet speeds. And again, an indication of a poloidal magnetic fields accelerating the jet, which expands in a parabolic shape before it becomes conical. So what would an alien observer see looking back? So if I just look at my sky map and try and find out where M87 is, I seem to remember. So 50 million light years in that direction. 50 million light years, my alien astronomer is looking back. What would they see? Well, the Earth, those continents have now split apart slightly. They're in the northern hemisphere. Or what would become the British Isles is in the northern hemisphere. Are there any humans around? The answer is no. The age of the dinosaurs come and gone, and there's just small mammals available on Earth. So my third galaxy I've chosen is Sombrero Galaxy. It's 30 million light years distance, so it's about half the distance again. And this is an optical image. I wasn't able to find a composite image. You can see why it's called a Sombrero Galaxy. And it's in the constellation of Virgo. And I believe you can observe this with relatively small telescopes, or if you're using a camera with exposure of a few hours, you can get fairly good images as well. And from those very long baseline interferometry images, you can see the core, and they've got, this is a part of the south jet, the north jet, various luminosity knots, and how they change in time over various epochs. Again, I guess you wouldn't necessarily have a uniform accretion rate from the black hole. So this changes the acceleration of the jet flows and changes those positions of the luminosity knots. So some of the things I've managed to find out, 1 billion solar mass black hole. It's a low luminosity AGN. It's got a lower temperature accretion disk. The event horizon radius is smaller. 3.5 light days as a radius for the base of the jet. Again, these expand out. They can be at parsec scales and even larger later on when, as you saw with Cygnus A, with the radio emissions, they can be very large before they terminate. So in terms of my alien observer, astronomer, what will he see? Will he be able to see the United Kingdom? Well, not really. 30 million years ago, it kind of looks familiar. North America and South America haven't joined together. India's got a bit more work to do, and Europe has got to get together. So not quite the British Isles. Oops, sorry. I haven't got my speaker notes. In terms of humans, are there any humans? The answer is no. You're right. So when I was doing my homework, I found out there's large mammals, but no humans still. And there's been various extinction events and global cooling events, etc. So no British Isles and not us. And I should have. So those are the three galaxies, the three examples of observations. But before I go on to talk about some of the research that we've been doing, I couldn't let go of my thought experiment. And I was thinking, what about the nearest large galaxy, which is Andromeda, which I showed you briefly earlier. So Andromeda is just 2.5 million light years away. And if I have a look on my sky map, excuse me for a moment. Okay. Oh. I think it was just about 2.5 million light years in that direction right now. So my alien astronomer could be looking back, and the photons of light that left 2.5 million years ago would be entering his eyes, observing, looking back. What would he see? Would he see the British Isles? Well, the short answer is nearly. Apparently, 2.5 million years ago, from what's known in this dark area, the British Isles is more or less where it is now. But the contours changed depending on rising and falling sea levels. And in doing my homework, I found out that the English Channel has only been around for 8,000 years. So the British Isles, yes, more or less. And how about us? So that's the question. Well, this is Homo sapiens. We're Homo sapiens. Homo sapiens have only been around for about 40,000 years. So you wouldn't be seeing Homo sapiens. So how about Neanderthals, the cavemen? Well, apparently Neanderthals have only first appeared about 1 million years ago. So how about Homo erectus? They only appeared about 2 million years ago. So actually, he or she would see Homo habilis, who I've never heard of before. So the answer to the question was, yes, they'd probably see the British Isles, but they wouldn't be seeing us. Yes?
How about if they're in a dwarf galaxy around the Milky Way?
I didn't think about that. I just thought about major galaxies. But you're right. If they're in a dwarf galaxy, it would be a lot closer. I'll come back to that. So I should have stopped my thought experiment there. And I'm a little bit sad that, this alien astronomer that we would have so much in common with, we're never going to get to meet. We're never going to get to share our experiences and observations. But then I thought, we had some clear weather over the British Isles just a few weeks ago. So light from the British Isles will be going towards Andromeda. So in 2.5 million years' time, an alien astronomer might see the British Isles and see us, perhaps. So that made me feel a little better. But then I thought, yes, but when he sees us, at that moment in time, what will the British Isles actually look like? What will we look like? Apparently, in 2.5 million years' time, the British Isles, along with the continents, will be beginning a journey back to form one large supercontinent centered on the equator again. And as for us, well, that's $1 million question. I don't know. But I think, in conclusion, I think from my thought experiment, I think I'm never going to get to talk to a fellow astronomer if I was an observational astronomer. If they were ever aware of us, I think they'd have to be in our galaxy, and even then, fairly nearby. So moving on to the last part of my talk about some of the research that we've done. If you're carrying out research, you normally start with a knowledge gap. So you start with a knowledge gap, and then you propose a hypothesis, and then you carry out research in order to substantiate or to prove your hypothesis. And actually, in research, even if you disprove it, you've still advanced knowledge. In our case, our knowledge gap was the fact that if you think how galaxies are formed from a coalescing hydrogen forming stars, and the galaxies grow, if you follow those calculations through, we should find when we observe galaxies, they're much larger than they are now, and they should be full of dead and dying stars, but they're not. And if you do some calculations and from observations of star formation rates, they are between 1 and 2 orders of magnitude lower than we'd expect. So between a factor of 10 and 100 lower, so much lower. So something is slowing this ingress of gas from the extragalactic medium to form stars. So that's the problem statement. So our hypothesis, this is with my supervisor, Professor Michael Smith, was that if you have these galactic jets and you send energy pulses along them, you might be able to send out enough energy laterally to heat the gas and slow its impact, and therefore explain these slow, lower star formation rates. So that's what we did in terms of energy pulses. We've noticed previously when we looked at steady state jets, which I said before aren't really steady. The flow might be steady state initially, but jets oscillate, shock fronts, etc. We found mostly that there was energy drawn into jets. And this is because the jets engage with the ambient, driving it out very far from the galaxies, and there's a backflow, if you like, of matter and energy. But there are some configurations where there's a net energy outflow, but it's very small. So we thought, well, what if we send velocity pulses along the jets? When it came to writing the paper in the Royal Astronomical Society, my supervisor, Professor Smith, thought he'd like to have a press release. So I worked with him on that and people at the Royal Astronomical Society. And we produced a press release, and the heading was, "How the Heart and Lungs of a Galaxy Extend Its Life." I've never been involved in the press before or anything like this. It's out of my comfort zone, but I kind of get it. They kind of want a catchy headline, rather like when you're writing a paper, to be honest. You want researchers to want to read your paper, and if you don't have a snappy title, so that was the title. So what I thought I'd like to do is just briefly talk about this press release and then go through a little bit of the research, and then you can decide for yourselves whether this press release was accurate or not. So it was Professor Smith who thought that in looking at these pulse jets that we had, we were sending out velocity pulses along the jet, and it meant that the shock fronts would move away because the jet's higher velocity and then moving towards us. And he thought of that as a pair of lungs, if you like. These Mach disks were moving back and forth, and you get that if you had a variation in the accretion rate in the central black hole. So if you high accretion rate, you get high temperatures, low accretion rate. So that's your central heart, if you like, your beating heart. And then the jet, when you have these Mach disks moving back and forth, rather like the diaphragm, thoracic diaphragm in a lung. And it sends out pressure waves into the ambient, energy waves, which can heat the ambient, just like we breathe out air in the surroundings. So that was the analogy. But like most analogies, it has limitations, but that's what we were choosing to use in our press release. So that's the thinking behind it. And basically, we found configurations where there was quite large energy outputs we found into the ambient, and they're traveling at the speed of sound in the ambient, 1,000 kilometers per second, which is faster than the cooling time. So it kind of all makes sense. So effectively, we've proved our hypothesis. It doesn't mean to say, so it is a solution. It doesn't mean to say it's the solution, just like, so many unknowns. So in terms of the research itself, very briefly, because there's so much that we don't understand about jets and a lot of gaps in our knowledge, we explore parameter phase space. So we look at jet to pressure ratios and jet to ambient density ratios. I won't go into detail, but we looked at pulse variations that were short, intermediate, and long, and amplitudes that were high and intermediate. So we look at all these variations, and we try to look at what sort of energy outputs that we could get. So effectively, we take a base jet, and we superimpose an energy burst. And these base jets, I won't go into details, but this is a low overpressure jet, and like I showed before, you get these reflection shocks, these oblique shocks. This is pressure, this is velocity, which is kind of the opposite, and density, and this is jet tracer. So jet tracer is basically white is jet material and black is ambient. So if you're losing some jet material, then you can see what's happening. So this is for a low overpressure, low density ratio jet. We believe that AGN jets, these galactic jets, are low density jets. Their densities are lower than the ambient surrounding them. And this is what a high overpressure is. As we expect, we've got Mach disks, but it's highly energetic, and even the steady state jet is sending some energy into the surroundings. So we looked at, like I say, short, intermediate, and long pulse durations. And we'd have something that looks a little bit like this. For a short pulse duration, the shock fronts are moving, are varying in the jet, and the pressure waves are extending out into the ambient. And there are observations of luminosity knots that are moving back and forth. So there is some observational evidence for that. So this is an intermediate pulse jet. So this is where we thought the analogy of a bellows effect, if you like, of the lungs, to try to get this message across. And then looking at a very long pulse duration. And these durations, these simulations are non-dimensional, so they can be used for any size jet, any size galactic jet, protostellar jet, jet engines, etc. And in terms of the choice of short, when I use the term short, medium, and long, these are in relation to characteristics of the jet themselves. I won't go into details, but there is a link between the characteristics of the jet and the timescales that we choose. And this was one of the jets where we had a very high power output. There was about a third the jet power was sent out laterally into the ambient. And effectively, what was happening is when we had these velocity pulses, sinusoidal changes in velocity. So you had a faster section of jet, which is catching up with a slower section, which is forming a compression, just at the time when the Mach disk is returning back along the axis because it's in a slower moving section, and you get this compression, sending a pressure wave out into the ambient. And we produced lots of graphs like these. Most of them weren't positive. This was very positive because of those characteristics that we found. So we did find about a third of jet power being sent out laterally into the ambient. And that is sufficient to moderate those cool gas inflows and try and explain the low star formation rates in galaxies. One of the other things we found in looking at these jets is that just look at the green peaks on here. This is mass flow going out laterally into the extragalactic medium. And it wasn't the purpose of the paper, because in the paper you have to focus on your hypothesis and you don't go astray. But it was an observation that this would mean that some of that jet material would end up in the surrounding ambient. And from observations of the extragalactic environment, there's a lot of metallicity, which basically means heavy elements. So elements that are created in stars, but they're found way out in the extragalactic medium. And this might be one mechanism for doing that. But like I say, for most of the jets, even the pulse jets, there was a net inflow of material into the jet, because the jet, just like the steady state jets, were engaging with the ambient, driving it out, and there was a backflow of material coming into the jet. So it might well be that in terms of explaining our knowledge gap, to explain the low star formation rates, it could be that there's mechanisms to heat the extragalactic medium, or it could be a combination of that and starving those inflows. So as the gas is cooling, it's been drawn in by the jet and sent out, recycled into large distances. So our conclusions were that for most jet configurations, there was an inflow of energy and mass, and that's what it was. For some jets, there are large oscillations in the standoff shock position. That's the first shock, that first Mach disk. And there are some observations in various AGN jets where the luminosity knots are oscillating over a period of several years. And then the key point is we did find some configurations where there was a significant lateral energy outflow. So that's a possible reason. So just for the last slide, just to recap, I went through some of the theory of AGN jets and how they're powered via black holes and some of the shock structures within supersonic jets to give you that background. From observations, I've picked on 3 relatively nearby galaxies that have jets, and I've shared with you some of my thought experiment. And then finally, a little bit about the simulations we've carried out in our research with our press release to begin with. The heart and lungs of the galaxy help to control its growth, maybe, and how we came to those those conclusions. So thank you.